So that's just going to continue our conversation with Marissa, our thin section extraordinaire, and her photography skills will amaze you. And I think Pat's going to help her out a little bit with some voiceover stuff, right?
So Marissa's been doing thin section photography, and this is done on a special polarizing microscope that uses transmitted cross-polarized light. And here's one of her beautiful chondrules.
Wow.
What all I mean?
Yeah, this is in Allende, and it is a complex polysomatic barred olivine chondrule. So there's sets of plates of olivine peridot, and those plates, when you look at them, in this special technique with thin section and with the transmitted cross polarized light, the olivine that is in the same crystal and lattice orientation is the same color, but we've got at least 3 different colors here, probably
At
4.
least.
And in each of those, the crystal orientation is different.
That's really spectacular.
Yeah, that's a beauty.
And next, we will jump over to this beautiful
Whoa.
PO chondrule.
PO.
These are so pretty. So this is a Poikilitic olivine.
Nice.
And Poikilitic is a $10 word that means big crystals and small crystals. And in this case, it means really, really big olivine crystals and crystals that are so small you can't see them, and actually they don't exist in the glass. So this is actually a bunch of olivine crystals floating in glass in a chondrule. And these chondrules are found more often in the more primitive type 3s and in some of the carbonaceous chondrites. And again, you see all the different colors in the olivine because these are each, individual crystals, and each have a different crystal orientation compared to the direction we're looking at it.
I don't think I'm going to get a better photo than that. This is extremely hard stuff to do.
Yes.
The lighting has to work, the camera has to cooperate, and the stacking has to work, and everything just came together beautifully with this one to get the entire field of view in focus, right to the edge. Normally, it's a little blurry all around the edges.
As was seen in my attempts at microscope photography earlier. But I've actually been to a very high-end art opening of thin section photography that was blown up into massive wall prints. And this quality of photograph, Marissa, is on par with that professional artist who was selling us stuff for a lot more than what you're charging us to look at it.
Yeah, the fellow who does that thin section photography had access to many tens of thousands of dollars worth of equipment to do some very, very specialized photography on gigantic thin sections.
Yeah, that would be a dream come true.
We just had a couple comments calling this stained glass chondrule, sorry. If you guys could roll through a few more of these pics, I'm interested in seeing some more.
Sure, this one is one of my favorites. It's NWA 4645. It is classified as an L/LL3.
Beautiful.
I just loved it. The olivine was all broken up and it just looked so beautiful. And I loved this one the most. It faded from a pink to a yellow. It reminded me of like pink lemonade or something.
Yeah, it's got great color texture.
These are beautiful, and one of the things that Marissa does with this that I think is so cool is she draws out the science in it, and is very founded in the science, but there's also, you know, a very artistic eye here, and this one, you know, in that olivine grain, and the other ones around it too, they're just some beautiful colors. And one can kind of do color composition by rotating the stage, because you know, as you change the angle of the crystals, you get different false colors or interference colors. So there's science and there's art in this, which I think is pretty cool.
More. Ooh.
Ooh. This one really caught my eye. I just love that there was a mix of a radiopyroxene up here, and then down here a couple of messed up, broken, barred olivine chondrules.
Yeah, these you know, these primitive type 3 unequilibrated, there's your $10 word for the day, meteorites are amazingly chaotic. You know, there are some big full chondrules, but there's a lot of broken chondrules, and I had a discussion with Alan Rubin. No, it wasn't Alan Rubin. It was the fellow from University of Washington, and I was concerned that some of the chondrules, you know, look busted up and stuff. And he said, you know, does that make it not primitive? No, well, it turns out it does. He says it was a very violent place. There was a lot of stuff smashing into each other. So even the primitive type 3s have a lot of broken chondrules in them.
I may be showing my ignorance here, but that's fine. I don't care. If you go to the first one, or go to the one that we were calling the stained glass one, I think. No, it was okay, yes. Okay, I want to dig into this a little bit, Pat. Help me understand. When you're looking at these different crystals through this process, I would assume that different colors would represent different chemical compositions, different minerals, different end. What you mentioned that, and I don't want to misunderstand you, you mentioned that it could be this, they're all olivine, we're just looking at them at different angles. So how in the world could this be used for diagnostic purposes if it's just the angular color shift?
Right. Excellent question with an extremely complicated answer, but I'll try and do the Reader's Digest version. So the minerals that show these beautiful false colors are birefringent. That means that light travels at different speeds depending on the direction that it's going through the crystal. So the angle of the light to the crystal lattice. And in this technique, the light comes from the bottom, it's polarized light, comes from the bottom, splits into the fast wave and the slow wave, and then they come out the top of the thin section, and you get constructive interference as a result of the difference between the fast wave and the slow wave. The color that you get coming out is about how those fast and slow light waves through the crystals recombine. So you get constructive and destructive interference. Mm-hmm. The colors that you see, so for meteorites, you know, most of the silicates that we see in them are either pyroxene or olivine. Pyroxene is mostly a black and white sort of thing without a wave plate or anything. It's pretty much black and white. Olivine gives us colors, and those colors are used for identification. You can also, and the thing that this technique was first invented for identifying minerals by their refractive index. And refractive index is just the difference in speed between the fast wave and the slow wave through the crystal. So, you know, we can we can measure the refractive index, but to put the whole thing together of how you get all the false colors and how you do identification and all that, I felt like I understood it once when I read it, and its sense has left the building, just like Elvis.
Yeah. Well,
So, sorry, that wasn't simple, but
no, with all due respect, the same thing is happening right now, and I'll be able to go back and replay what you just said and get it on the third time probably. So I encourage everyone, if Mike is going over your head, or Pat's going over your head, or I'm going over your head, feel free to rewind, play it again, and then if you have any questions, drop them in the comments, and we'll try to get to them. So, Marissa, I want to see a few more slides if you don't mind.
Yeah, sure thing. This one is a split image. How
Nice.
I'm
Yes.
expressing myself artistically and bringing out not just the science, but artistic side and the beauty of these thin sections and the beauty of all these meteorites.
That is gorgeous. So you can see the vertical line down there. That's with two different filters.
Yes.
Okay.
The filter on the right side is just plain cross-polarized light. The filter on the left has been, I added a full wave plate.
And the wave plate is basically a slice of mineral that is a certain thickness, so that you get, in this case, a full wavelength at some particular. I think it's 445 nanometers, but I'm not positive exactly what the color of light is. But it adds some more birefringence to it, and you get some prettier, wilder colors. And you can use this to look at first order, second order, third order interference colors. But this chondrule is, I think, is really pretty as well, in that, you know, it's a barred olivine chondrule. We can see all the plates there that you know, are a consistent color. So you know, even though, you know, we've got the wave plate in on the left, but they're all the same color and all in the same crystal orientation. And in between those plates of olivine, and by the way, these are plates, so you know, we're looking at a cut edge through the end of it, but you can imagine a stack of plates, and you cut down through it, and you'll see the edge of each plate. And so in between, there's glass, and glass, because it's not birefringent, the speed of light through glass is the same in every direction. It comes out black in these transmitted polarized light photos. But you can see the inner part of the chondrule where the bars are, and then you can see an outer ring of the chondrule that's really thick and has some areas in it that won't pass light, and those are probably opaque for a different reason. They're metal and iron sulfides, most likely. But the conditions in the protoplanetary disk are really amazing. So, you know, we've had chondrules that are melted little cosmic dust bunnies, but there's all sorts of other processes that go on. There's vapor of things in the protoplanetary disk that condense out on the chondrules, and so they get these rims built up around them that are pretty, and they tell us something about the protoplanetary disk.
Pat and Marissa, thank you so much for tag teaming us on that. Beautiful science and art all mixed together. Really appreciate it.